recording. So we are now recording, and I will put the correct class on the projector. That's the wrong class. I mean, eventually you have to take a 310, but depending on your major. But if you're computer science, you have to take 310 anyway. All right, so we are good to go. So let's go back to the announcement because I gave you guys a kind of informal homework assignment, and then we'll also go through binary search if you guys want to go through binary search in today's lecture. So we'll start with algorithm for calling and returning first, and we'll trace that, and then we'll go back to binary search. Yes. hmm So we always, in this case, we return to the line that is following the line that contains the invocation of the function. So, okay, so that's a good way to start today's lecture is to differentiate between a few concepts here. Lines one and two is they are the definitions of function f. In other words, this is how we say, oh, function f when it is invoked, it has got these things to do. Okay, but in this case, function f and g are both empty, which means well, you can invoke them all you want, but they're not going to do a single thing. There's simply nothing to do. Line 7 is the invocation of G. Line 8 is the invocation of F. And then line 4 is also an invocation of F. So when we trace this code, F is going to be called twice, okay? Once directly from main and once indirectly from function G. Yes, go ahead. Mm-hmm. Correct. That is correct. So what we'll do is we are going to trace the code. Okay, so hopefully you guys got a chance to do it on your own. And what I will do is to put it on to the shared drive or the shared folder. So this way, if you want to check out the recording, I mean the actual trace, you can do so. So this is all in CISP 300 in the shared folder that you already have access to, and I'm just going to create a spreadsheet or a Google Sheets for today's lecture. And the first sheet is going to be, the trace of the algorithm that was displayed. Okay, right here. Make it always on top. So this way, okay, I just click on something else. Nope. Come on. Here, there we go. All right, so let me clean up this part a little bit here so we can have more real estate on the screen. All right, so now we are ready to trace the code. And at this point, I use, column A for comments, okay, simply because the number of columns that we actually need to use is dynamic, okay, because, we allocate and then we deallocate and we allocate and we deallocate. So that's why I move comments to, kind of the first column. Line number is going to be the next one. And that's all we have to begin with. There are no variables whatsoever in this entire program. So we don't need any columns for the variables. So the first line is still going to be a pre, okay, which specifies what do we know before the program executes. In this case, absolutely nothing. There's nothing to know about in this case because there are no variables to begin with. And then the first line that we start execution is going to be the first line of the definition of main, okay? Because the main function is called main because it is the entry point of the entire program. So execution starts on line 6. And I'm going to shrink the column here a little bit because we don't need that wide of a column. And then execution proceeds to line 7. Line 7, if you look at the code here, is the invocation of G. So can somebody remind me what do I do when I invoke a function and how do I trace the invocation of a function in this class? There are like three things to do. Okay, so there are three things to do. Tell me step one, step two, step three of what happens when we invoke a function. Hmm? We So we allocate a new column first. Okay, first step, allocate a new column, label it as return line number. In other words, we're using column C in this case to help us remember when this function is completed, where do we go to continue execution? That is the purpose of return line number, in this case, column C. The second thing we need to do is to actually remember where we're supposed to go back to. So we are talking about line 7 invoking function G. So when function G is done, where do we go back to? Which line do we return to? Yes, line. Yeah, that's just line 8. Very good. Okay, so it's line 8. And then the third thing that we do when we invoke a function is to continue execution at the beginning of the function itself, which is in this case, which line? Which line is the first line of function G? 3, that is correct. Line 3 is the beginning of function G. So these are the three steps when we invoke a function. All right. So this is actually documented as well in the module. So hopefully, you guys had some time to read from the module or to revisit the lecture from before the spring break because that's where we left off before spring break, I think. Is it after? So it's the Monday after, right? Yeah, unfortunately, we had a break on this Monday, so it has been a week since last Wednesday. It was Wednesday. All right. So, yeah, this is why personally I do not like to have a long break followed by a really short break because we lost a class nonetheless. All right, so now continue on to line 3. Line 3 really doesn't do anything, okay, but line 4 does. So line 4 is the invocation of function f from inside G, okay? So we just mentioned the three things that we need to do to when we invoke a function. Can someone read from your notes today of what we need to do? What are the three steps that we need to do when we invoke a function? We start with step one. What is step one? This time we have to allocate column D, okay? Because column C is in use right now. We cannot use it again at this point, okay? It is in use already. So the next available column is column D. So column D is now quote unquote allocated and it is labeled a return line number because that is what we do for every function call, okay? Is to allocate the next available column. Remember where we need to go back to. The invocation is on line 4 here. So where do we go back to? Which line do we return to when the invocation of f is done on line 4? The next line available. What is the next line available? 5. Line 5, okay? So line 5 goes here, okay? So that's kind of important, okay? Because the line number that you put in the column that is labeled return line number is the one that is usually just logically following whatever line that contains the invocation itself, all right? And then what was the third step again? When we invoke a function. The third step is to continue execution at the invoked function. So this time we're invoking function f. What is the first line of the definition of function f? Look at the code. Look at the actual C code. So where does function f begin? Line 1. Okay, so that's why we continue execution on line 1. All right. So let me just kind of pause right here and see if there are any questions about the trace up to this point. Main calls G, G calls F. But every time there's a call or invocation, okay, so call and invocation are really the same thing, or invoke are the same thing. So every time you invoke or call a function, there are three steps. Allocate a column, Use it to remember where the called function is supposed to return to when it is done, and then continue execution at the beginning of the function that you are invoking. So those three steps are always going to be the same, no matter where the call is from and no matter what the function is actually calling. Are we okay with those concepts? Is that okay? All right. Yeah. So now that we are at on line one, we just logically continue on to line two. Function f doesn't do a single thing. So now we're on line two. So on line two, we are ready to return because line two has, this concludes the execution of function f. Okay. So now the question is, when we return, what are the three steps that we need to do? So when we call, there are three steps. When we return, there are also three steps. They're kind of like exactly the reverse of the three steps when we invoke a function. So what is the first step we need to do when we return from a function call? The first thing is, yes, find which return line number column to use first. Okay, so how do we know whether we should use column C or column D? Okay, it is in the notes. Okay, in the notes, what does it say about which return line number we should use when there are multiple return line numbers active at the same time? The rightmost return line number that is not deallocated. So can someone tell me which one is the rightmost return line number that is still in use right now? Just name the column. That will be column D. Very good. Okay, so we locate the rightmost return line number column. Look at the line number that we remembered from earlier. Copy and paste that to the next row, the line number of the next row. So now we all we need to do is to say, oh, this is referencing this number here. This is also line 5. That's the first step. Okay, second step, sorry. First step is to locate. Second step is copy and paste the line number. Third step is to deallocate the return line number. So that what that means is you simply copy and paste the heading of the column and then you mark it as deallocated. There's a shortcut key that I cannot remember how to do it, so I'm going to look it up here. You can go to text and use a strike through. So it's Alt Shift 5. Okay, so I'm going to practice that and use Alt Shift 5 when I'm on the cell. Alt Shift 5, and now we have a strike through. So the striking through is an indicator that this column is now quote unquote deallocated, which means it can be reallocated at a later point if I need it. Okay, so I'm going to pause again to see if there are any questions about what we have talked about so far, which is calling, and then we have returned once already at this point, and then execution is now on line 5. Are we good so far? Okay, all right, very good. So now that we are on line 5, what does line 5 want to do? Well, line 5 has nothing to do other than, oh, we are at the end of an invocation again, so we have to do the same three steps again, okay? Hopefully you have written down from today's note what to do, what are the three steps that we need to do when we return from a function. A function has completed already, we need to return. Step one, locate the rightmost column that is named return line number that is not deallocated. So between column C and column D, which one should I use? Which one is the rightmost column that is labeled return line number that is not deallocated? Yes, column C, that is correct. So we now know, okay, we need to make use of column C. Second step, look at the line number that we remember earlier, which is line 8. Copy and paste it to the line number column of the next row. So now this row is going to refer to this number here, which is reminding us that execution continues on line 8. Okay, after these three steps. So that's step number 2. What is step number 3? Starts with a D. Deallocate the return line number. Okay, so now we have to remember this column is no longer of use for me because I have just utilized the information that I have stored in this column. So once again, I need to deallocate, which is really just copy and paste the cell that is, telling us what the column is about, and then use Control Shift 5 on the keyboard to strike out, the labeling to so that we can mark that this column is no longer in use at this point of time. And then execution once again, continue on to line 8. So let me pause here and see if there are any questions about the process. This trace is unique compared to the trace that we did on last Wednesday, because the trace that we did on last Wednesday was using the same column, right? Because we have two consecutive invocations of f. In this case, we have a nested call. Main calls G, G calls F. So F has to return to G first. And then when G is done, then G returns to main. Okay? So do we have any questions about the trace up to this point? No questions? Okay. Okay, I can give you guys a little bit more time. Does anyone need more time to think about what question to ask? Does anyone need more time to think about whether they need more time to think about what to ask? Okay, I just did a little recursion on the question itself. Nope. Okay. All right. So now we move on to line number 8. Line number 8 says, oh, I want to call f from here. It is perfectly okay. There's no restriction as to what function you can call from which other function. Main is free to call G. Main is also free to call F. Okay? Even F is free to call F, even though that is not the case here. So we're going to talk about recursion, when we get to that point. Okay. So line 8 says, oh, we need to call F. I know this is going to be super boring. Hopefully it is. What do we do? What are the three steps when we invoke a function? Okay, very good. Okay, let's pause right there. What is the next column that is available? What is the next available column to the right-hand side? Nope. Column C is now available again because it had been deallocated. So the leftmost available column for us to allocate is actually column C. Is that okay? So that is the whole point of deallocating a column, is so that we can reuse the column later on. Okay, so we allocate when we need it, but when we have no need for that column anymore, we remember that that column is now deallocated so that we can reuse that same column. Is that okay? So that is the reason why we can now reallocate column C as the return line number again. What role a column serves is not necessarily the same. I can reallocate it for something else, okay, but we haven't really talked about local variables yet, so it has to be a return line number in this case. What about the second step in calling a function? Once we have allocated a column for the return line number, what value do we store on that column? In other words, we are talking about line 8, calling f here. So what do we write down, in this cell here, so that when function f is completed, it knows where to go back to in main? What line number should it continue on to? 9. Very good. Okay, very good. And then what is the third step? Continue execution on the first line of the definition of the invoked function. So what is the first line of function f? Yes, line 1. That is correct. Okay, so we go back to line 1, which doesn't do a single thing. Then we go back to line 2, which is the completion of the invocation of function f. So I know this is going to sound really boring because it should be boring. Um, what do we do? What are the three steps that we need to do when a function is completed and it needs to return? First step, locate the return line number, the rightmost return line number that is in use. So which column should we use? Okay, but column D is deallocated. It's not in use right now. We only have one column that is labeled return line number. It is column C. Column D is now deallocated. It is out of commission. It's not being used at this point. So it is column C. And what is the second step? We utilize the return line number, okay, and what line number is already stored here so that we know, oh, the next line has to be line 9. So basically, whatever this line is, we copy it here. Oh, okay, it just did something that I did not want it to do. Oh, actually, it does. Okay, um, there we go. And then what is the third step when we return from a function? Okay, it should be in your notes now because this is like the second time we do this. Okay, we just located the rightmost return line number. We just made use of whatever is on that column. What is the third thing that we need to do when we return from a function? What do we do with the column that is labeled return line number? Yes, cross it out to deallocate it. Okay, that is correct. So we basically just use the label, put it here, and then Control Shift 5, strike it out. So now it is marked as deallocated. Line 9 is a return 0 of main, and typically we don't trace, there's nothing else that we need to do on this line, so post is right after that. So this is the entire trace of this program that does not do diddly jack. Yes, that is correct. The focus of this entire useless program is on the mechanism of calling and returning. So are we clear on that concept? Let me name the spreadsheet first so it's easier for you guys to locate this later on. It is based on just today's date, so you can always just locate it. Are we good so far with calling and returning? Mm-hmm. Correct. Yes. It also helps if you know where to find the notes. So I'm going to help you do that. So we go back to the class code here, or the class, and then we go down to um, array. Okay, control structure is all done. Okay, so I can collapse that whole thing. Array is pretty much all done, but I don't want to collapse it because I do want to talk about the solution to the binary search assignment. So we are now down to subroutine. This is the module that we used on last Wednesday when I described how to invoke and how to return from a function. So everything that we did today is based on that. Today is more or less just an example of reusing the concepts that we have learned on last Wednesday, just to go like, oh, the program looks a little different from the example in that particular module, but the concepts are exactly the same. The steps are exactly the same. So I think from looking at the facial expression, I think the confusion part has to do with what is allocating and what is deallocating. So I can do one thing to help emphasize, what is allocating and what is deallocating. I can use some highlighting here. So I can say that this portion, these cells, together is, when starting with the allocation and ending with the deallocation. And what I can also do is I can fill the color of the background a little bit, just so that it is visually, we can see how the allocation works here. From here to here is also, the lifespan of those particular cells. In other words, that is, this is the duration of when column D is in use. So column C is no longer used on row 11, so it is available again to be allocated and then deallocated later on. So this is, I'm using yet another color here, just so that we know when did we allocate, when did we deallocate, when did we allocate, and when did we deallocate. So I hope this color coding helps a little bit in terms of what I mean by allocating and also deallocating when we reference these columns. Is that helping or not? Okay. All right. Very good. All right. So are we ready to move on to the? Oh, we have to go back and talk about binary search, so I can do that. But before we move on to binary search, do we have any additional questions about the mechanisms of calling a function? And when the called function is completed, how do we return from the called function back to where it was called in the first place? Do we have any questions about the concept, the mechanism, and also how those particular things are traced in a spreadsheet like this? No questions? Okay, all right. So I'm not accusing anyone of not, kind of reviewing the material, but I do have to re-emphasize that it is important to review the material. This class is, I hope nobody, thinks too negatively about what I'm about to say, but I have to be honest. This is a baby class in programming. Okay, this is a very quote unquote gentle curve, stepping into programming. So that means um, studying or reviewing the material in a class like this is important, okay? Because the pace at which I'm introducing the concept is considered to be kind of slow, okay? Um, and if you want to have some references as to why I say that, or by what standard do I use to say that this is a baby class and it is a little bit slow, I took computer science classes in 1985. Okay, yes, I'm that old. There is no CISP 300. There's no CISP 360. Back in those days, the first programming class is what is equivalent to our CISP 400. Okay, so that means there is, and it is still just a one semester class. Okay, so it's not like oh, we have a longer class or a higher unit count class. It's the same unit count as your CISP 400. In fact, it is 1 unit less. There's no lab component when I took what is equivalent to CISP 400. So by that standard, okay, which is what UCs typically do until very recently, we have a somewhat gentler learning curve when it gets to introducing to programming concepts. Yep. So using the compiler, you can write some code and you can run it and see what it does. You wouldn't know how it gets the job done. And to me, it is always the fundamental that is more important, understanding how it gets the job done. And then you go like, oh, okay, once I understand what tools are in my tool belt or in the toolbox, then I can, figure out how to use those tools in order to create something. As opposed to, oh, I'm just gonna take my power saw and power drill and just randomly do some stick stuff to the wood and see what happens. So um, I think it is important because I was a TA in 1990. Okay, that's when I started my graduate school. So in 1990, when I was a TA at UC Davis, um, I was basically a TA for a class like CISP 400. Okay, in other words, that's their version of a baby programming class. That's their version of a beginning programming class. And when I saw people writing their program as a homework assignment, and the code is not working, do you know what they do, what the students did when their program did not work? They started to make random changes to the code, which is probably the worst thing you can possibly do in order to figure out how to repair something that is broken. So you can kind of imagine that let's not talk about programming. Let's think about the cars. Okay, so back in the older days, your cars have a lot of vacuum lines in order to do the control, right? So let's say your engine is not running. Okay, you try to start the car and it won't turn. Okay, so people just start to unplug things and then plug them somewhere else. What are the chances that these actions would actually improve the situation? Exactly. It's usually going to make it worse, especially when people do not take a picture of how things are hooked up to begin with, so they cannot even restore to what it used to be. Okay? That's what happened at UC Davis for their first programming class. And people did that because they did not have the mindset of, okay, I need to understand why the program is misbehaving. They may not even have the idea of what is this program supposed to do. By the time it gets to this point, what am I supposed to observe? If they don't have that idea, they cannot debug a program. Okay, so that's why when I teach this class, I start with the fundamentals, which is how do things work behind the scene. Okay, so that people understand. Oh, so this is what happens when we call a function. This is what happens when the function returns. Now, is this unique to C and C++? The answer is no. This applies to just about every programming language out there. You can use JavaScript, you can use Java, you can use Python, you can use Visual Basic, C Sharp. They all have pretty much the same mechanism when it comes to calling and returning. So you know, when I explain the mechanism and trace it in a table like this is applicable across essentially all programming languages. And the way this is explained also makes it a little bit easier when people get to CISP 310, because the same concept is going to be explained in just a little bit different way, but the same kind of method. It's just explained using different terms. Yes, please go ahead. So all programming languages are artificial constructs, which means they're made. They're designed and engineered by either a single person in some cases or a group of people internationally in some other cases, but they're all artificial constructs. They're all invented. They're all created by computer science people. So that's a good question. So any other questions or comment up to this point? Okay, because I really do want to explain the grand scheme of things, how this class compares to your career plan to become a software engineer. I know not everybody in this class is you know has the objective of entering the computer science software and tech world exactly, but it is I would still say the majority of you have that goal. So you need to kind of understand what does it mean to get to the end of the educational goal. All right, well, that reminds me, what is your educational goal? Why are you here? I mean, we see all the signs around the campus, you belong here. Okay, and as much as that is important, why are you here? To be more specific, why did you choose the computer science program? For those of you who did choose the computer science program, because I know some other people in this class, the minority have to take this class because their major is requiring this class. Okay, so if you're one of those people, you can tell me what program you're in and why, which program requires CISP 300 as part of your program. So I know Chem E, chemical engineering is one. So what other ones? Yep, go ahead. Electrical engineering. So electrical engineering is actually really close to computer science. So there's a spectrum. Electrical engineering is more leaning the most on the hardware side, but it doesn't have to be. And then there's computer engineering, which is kind of sitting right between electrical engineering and computer science. And then on the software side, we have computer science. So those three are kind of closely related. I know people who basically just segue, along their career path, one way or the other. Exactly. So I started off with computer science and I segued, definitely into computer engineering and a little bit of electrical engineering. I know people who are electrical engineers who segue back the other direction to become computer science or software developers. So definitely related, and important in this case. Anyone else? Nope. Okay. So I know, I have been talking about this. I don't want to people to think it is doomsday. So what happened in um, software development in terms of employment? What is happening with that scene? Yes, yes. So the pandemic, caused some of the tech giants to overhire. Exactly. Okay. So we got three things compounding at least. Okay. Three things that I can count right now. First one is the pandemic. During the pandemic, tech companies overhired. Okay. That's the first thing. What happened during the pandemic in terms of colleges and universities? Went online, exactly. Okay, so it was what, 2019, I think, 20? Yeah. So, suddenly overnight or over a week, over a weekend, okay, all the classes went from in person, all the in-person classes went online. For how long? How long did the pandemic last? More than a year, okay? More than a year. So during that time when all the classes are online, what do you think happened? What happened to all the exams of the classes? They're also online, right? And what happened, do you think happens with exams that are now online or then online? Yes, okay. But one thing that people noticed from the STEM field was the number of academic dishonesty skyrocketed during the pandemic. Well, in one way or another, a lot of people took the shortcut. Okay. So now you have two things at least compounding. You have overhiring during the pandemic, and two, you have people graduating because they were taking the shortcut. Okay. So the overhiring was hiring many of these people. And then the pandemic ended and the companies go like, "Oh, okay. So where's the productivity?" Okay? And then the third thing happened to compound on top of all of these. In 2022, what happened in November? AI. That's right. OpenAI released ChatGPT 3.5. Okay? And shortly after, Microsoft integrated that into their Copilot, which started to write code. Okay, so now you have the third component compounding on the first two, and that was to 2022. Last year, 2024. Does anyone know the company Salesforce that has a home base in San Francisco? Okay, so you drive on the highway, you see the advertisement, right? Right after you cross the Bay Bridge, it's like, oh, Salesforce. Okay, last year, 2024, in December, they said, oh, because of AI, they're going to have a hiring freeze in 2025. They won't be hiring new people anymore in 2025 because AI has improved the productivity of their existing employees. What did they do last month? They laid off people. So not only did they freeze the hiring, they started to lay off people. Existing people that were employed in 2024 were laid off. What about Meta? How many people did they lay off in the last batch? More than 3,600. Okay, and they're all mid-level software developers. They were not laying off only beginning level, but mid-level software engineers. Okay, so you have to look at this big picture and ask yourselves, okay, how do you, after you graduate with a bachelor's degree in computer science, how do you get into employment? Okay, because your bachelor's degree is not an automatic ticket to be employed, not even close. So I have to be honest. I don't want to tell you guys, hey, if you believe in something, it's gonna happen, because that is not how the world works. So you have to start to think about all of those things. Okay. So having said all that, I hope you guys are not discouraged, because that was not the purpose. The purpose is to help you guys prepare for your future. Okay, your career future. All right. Any comments back from any one of you? Anyone wants to share any information, opinions? Like Tack, you're just hallucinating like AI, because I think the job market is great, and I'm going to start to make $120,000 within a month of graduation, and within half a year, I'll be making more money than you do. Well, you can come back to me and, kind of tell me about how you're making 130K per year. I'll be happy to, listen and, hear back from my students, making more money than I do. I mean, honestly, really, I do. Okay, so if you start to make a lot of money, come back to me and tell me, oh, things have been great. I actually love to listen to those stories. All right. So having said all that, okay, we are gonna go back to um, the previous homework assignment, and we'll take a look at the solution of that homework assignment. So that's binary search, and the source document is right here. And I am just going to create the solution here, okay? Which means I cannot use the same homework assignment next year, but guess what? This is a one-off thing. I usually do not teach CISP 300, so I'm not too concerned. All right, so this is trace one. Okay, so the first thing is I need to take a snapshot of the algorithm first, okay, because I need to refer to the line numbers and stuff like that. So I'm gonna take a snapshot of this and put all this on top. Okay, stash it over here. And trace one, has a specific precondition. And then when we start execution on line one, we have to say, okay, B gets a value of 0. On line 2, E is n minus 1, n is 5, so E is 4. On line 3, we are starting the loop. So I typically do not trace line 3, okay, because there's really nothing to do over there. So we start with line 4. If you trace line 3, I'm not going to mark it wrong. It's just not necessary. So line 4 says we need to compute B plus E, the whole thing divided by 2. 0 plus 4 divided by 2 is a 2. And then on line 5, we have a condition to evaluate. So we have to go to comments and evaluate the condition on line 5. A bracket m is less than k. So now we have to look at, okay, what is the value of m? M has a value of 2. So a bracket m is referring to a bracket 2. A bracket 2 has a value of 3. K has a value of 4. 3 is less than 4 is true. Okay. So that means where do we go next? From line 5, where do we go next? If we get line 6, because line 6 is the then statement corresponding to the conditional statement starting on line 5. So line 6 has one thing to do, which is storing m plus 1. M is 2. 2 plus 1 is a 3. So B is now becoming 3. And then after that, where do we go? This is a little bit of a tricky question because it depends on whether you understand how to read nested statements or not. So after line 6, where do we go? Yes, the condition is true. We just finished the statement corresponding to the then statement, which is which happens when which executes when the condition is true. So we skip the else statement. So the else statement corresponding to the if on line 5 consists of line 8 and 9. So that means I am done. There's nothing else to do. We go all the way to line 10. That is correct. Hmm. Yep. This is a while. Right. So we get to line 10, and we now have to evaluate what is on line 10, which is b is less than or equal to e. Is that true or not by itself? If you look at the value of b, it is 3. If you look at the value of e, it is 4. 3 is less than or equal to 4 is true. Okay? So that means in the case of an and, we have to evaluate the other side because I cannot determine whether the and is true or false just by looking at the left-hand side because the left-hand side is true. So now we have to look at the right-hand side as well. So the right-hand side is looking at a bracket m does not equal to k. M is still 2. A bracket M is referring to column J, which has a value of 3. K has a value of 4. 3 does not equal to 4 is true. So now we have true and true, which is true. That is correct. The entire thing is true. So now where do we go? Not yet. We go back to line 4. That is correct. Because in a do while loop, okay, you can look at the word while and replace it with as long as. Okay, so that means whatever condition is specified in the while, if it is true, then we have to go back because we have another iteration of the loop to perform. So now we go back to line 4. Line 4 is going to compute b plus e, which is 3 plus 4, the whole thing divided by 2. But we truncate the fractional part, which means if it is 3.5, we truncate the 0.5. So we only have 3 left in when we assign that value to m. Is that okay? All right. Then we move on to line 5 again. Line 5 has the same condition to evaluate, which is a bracket m is less than k. M is now 3, so a bracket m is a bracket 3, which has a value of 3 again. So 3 is less than k, which is 4, is true again. So that means we have to go to line 6. Line 6 is going to compute m plus 1, which is 4, and then store that to b. So b is now 4. And once again, after line 6, we have nothing else to do in the loop, so we go all the way to line 10 again. On line 10, we are going to evaluate the same condition. B and E are both 4 this time. B is less than or equal to E is true. But since the left-hand side is true, we now have to evaluate the right-hand side. A bracket M does not equal to K is also true, so that means the entire conjunction is true. So we have one last iteration to go through. Go back to line 4, and then we compute m again. So this time m is going to be 4 plus 4, the whole thing, which is 8. 8 divided by 2 is just 4. So now we go to line 5, and then we now evaluate the condition of line 5, which is a bracket m is less than k. M is now 4. So a bracket m is a bracket 4, which has a value of 5. K is 4. 5 is less than 4 is false. So where do we go next? Line 8 is correct. Okay, so line 8 is the beginning of the else statement corresponding to the conditional statement that starts on line 5. So line 8 is where we go. And line 8 has its own condition to evaluate, which is a bracket m is greater than k. That is true because 5 is greater than 4 is true. So now where do we go? Sorry? Line 9 is correct, okay? So line 9 says here we want to compute m minus 1. So 4 minus 1 is a 3, but this time we do not store that to b, we store that to e. So e is now updated to a value of 3. And then we get to line 10. So when we get to line 10 this time, b is less than or equal to e is false. And that's all we need to know. Because in a conjunction, which is an AND, if one side is false already, the whole thing is going to be false. So that means using the short circuited evaluation, I don't really need to evaluate the right hand side of the AND. With this homework assignment, if you also evaluate the right hand side, at least in the trace, I'm not going to mark it wrong, but in reality, it's only the left hand side that is evaluated. That is already enough to tell us that the conjunction is false. Is that okay? Okay. So now that means we exit the loop after line 10. We got one more thing to do because found there's an assignment statement for found. The assignment statement for found evaluates a bracket m equals to k. So we look at m has a value of 4, a bracket 4 is a 5. 5 equals to k, which is a value of 4, is false. So found has now a value of either false or 0. So you can put a 0 here, you can put false here, both will be considered correct. And that concludes the execution of this particular trace. Yes? Mm-hmm. Mm-hmm. It is after the while loop because it's supposed to happen on line 11, which is after the loop. Yeah. Oh, you put it here as well? Yeah, that would not be correct. Okay, so I have to deduct some points because of that. Yeah, but if you get the rest of it right, you still get the majority of the points. Because the reason why I have to take off some points is because line 11 is technically not a part of the loop. So it does not execute. Line 11 does not execute until the loop has concluded, which means until the while condition is false, we do not get to line 11. Okay? Yep. You did not include line 10 to. Okay, but then the question is, how do you know that you need to go back? Without evaluating line 10, what is the reason to go back to line 4? So I still have to deduct some points because the formatting that I use in this class is you have to indicate the condition when there's a decision to be made. So the formatting is wrong. Okay, I still have to deduct some points, but as long as you you perform the iterations the correct number of turns, you still get most of the points, but I still cannot consider it to be a perfectly correct solution. Hmm. All right. So do you guys want me to go through trace 2 and 3, or is this sufficient to kind of demonstrate what is needed to trace through this code? It's up to you guys. I mean, I can do either way. Hmm. Okay. Yeah. Well, I want the class as a whole to kind of vote on this. Yes, no, maybe. Yes, as in we want to trace number 2, or yes, as in we can move on to. Okay, we'll go trace 2. Okay, that's all good. Trace 2. Okay, so we start with line 1. B gets a value of 0. 2, E gets a value of 4. Line 3, oh, we don't trace line 3. Line 4. So now it is the same. So the first few steps are about the same. Now we get to line 5, and we evaluate the condition. So now we have A bracket M less than K. K this time is a 6. So 3 is less than 6 is definitely true. We get to line 6 here. And then we update b to be m plus 1, which is now a 3. We go to line 10, and b is less than or equal to e is true, and we have to evaluate the right-hand side. A bracket m does not equal to k is also true, true and true is true. So we go back to line 4. When we get back to line 4, m is updated to 3 plus 4, which is 7, divided by 2, which is 3.5, and then we truncate the fractional side, so it is just 3 here. We go to line 5. A bracket m is a bracket 3, which has a value of 3 again. 3 is less than 6 in this case is also true. So we go to line 6. B is now updated to 3 plus 1, which is 4. Then we get to line 10, and then the condition is B is less than or equal to E. That is still true because 4 is less than or equal to 4. A bracket M is A bracket 3, which has a value of 3, and it being and that being not equal to K, which is 6, is also true. So we get back to line 4. 4 plus 4 is 8. 8 divided by 2 is 4. So now we move on to line 5. A bracket m is now a bracket 4, which has a value of 5. 5 is less than k, which is 6, is true. So this is where the execution starts to deviate from the previous trace. And in this case, we have to get to the else case. Oh no, we go to the then case. So now we add 1 to 4, it becomes 5. B is now updated to a value of 5. We get to line 10. B is less than or equal to E is false because B is greater than E in this case. So this is false. That is enough reason for me to exit the loop. Then we get to line 11. Line 11 is asking, is found, A bracket M is A bracket 4, and which has a value of 5. 5 equals to 6 is false. So we put a false here again, and then we get to post. All right. So I can do trace 3, kind of fast forward it a little bit. Okay. Is that okay? All right. So we get to trace 3, starting on line 1. B is 0. Okay. The first few steps are the same. This is 4. And then on line 4, K equals to 2, M equals 2. So these steps are the same. But when we get to line 5, things may be a little bit different. So this time we are evaluating A bracket M, which is A bracket 2, which has a value of 3. 3 is less than K, which is 1, is false. So we get to line 8, which has a different condition to evaluate. Oh, okay, let me fix this. This is intended to be K. So the other condition on line 8 is A bracket M is greater than K. It is true. And then we get to line 9, which updates E to be M minus 1. So E is now 1. We get to line 10. So on line 10, B is less than or equal to E is true. And then A bracket M, which is A bracket 2, which has a value of 3, not equaling to K, which is 1, is also true. True and true is true. We get back to line 4. So now we have 0 plus 1, which is 1. 1 divided by 2 is 0.5. If you take out the fractional part of 0.5, you get 0. So now m is updated to 0. On line 5, we are now comparing A bracket 0 because m equal to 0, which has a value of 1. Oh, okay, so this time it is found. So A bracket m is less than k is false because 1 is not less than 1. And then we get to line 6. Nope, we go to line 8. Okay, so we get to line 8. The comparison is now the opposite. Is 1 greater than 1? That is false as well. So now we have nothing to do except to skip to line 10. So when we get to line 10, B is less than or equal to E is true. But A bracket M does not equal to K is false. So that means the whole thing is false because the right-hand side is false, even though the left-hand side is true. So I just want to fix this code here. So we exit the loop at this point. We get to line 11. When we get to line 11, A bracket M is still referring to A bracket 1, which has a value of 1. 1 equals 1 is true. So this is the one where the answer is actually true. So this is actually different from the other two traces because we found the value that we were searching for. Yep. Hmm? Trace 2. So trace 2 has a conclusion of false. Well, this is all visible to you guys already, so you can kind of cross-check this against your solution anytime you want to. Yep. Are we good? Okay. Yeah. So with this code here, the one of the most important part of reading this code is knowing how to read nested statements. In other words, the conditional statement that starts on line 5, line 6 is the only then statement corresponding to the if on line 5, but the else is line 8 and 9. So when we skip the else part, we're skipping both line 8 and 9 when the condition of line 5 is true. I think we talked about how to read nested conditional statements. I gave you guys a diagram, and then we also went through the BNF representation to kind of look at how which statement is nested within which statement. So that should be applied when we follow this code in this particular program. Are we okay, or do you have a question? We good? Okay. All right. All right. So I'll give you guys a moment here to see if there are any additional questions about this particular program. And if not, then we will go ahead and continue to talk about local variables. Does anyone think you might need more time to formulate your question about the binary search algorithm? Okay, all right. So then we shall move on to local variables. That is correct. Yeah, I want to give people enough time to think about whether they have a question to ask and also to think about how to formulate the question because I know some people who would ask, "Do we have any questions?" And then within 2 seconds, it's like, "Oh, okay, let's move on." And I was really just about to open my mouth to ask a question. They go like, "Okay, let's move on." So I know how annoying that can be. So I try to give people enough time to think about the questions that they want to ask. All right, so we are moving on to local variables, which is a rather short module, okay? But the trace is interesting nonetheless, okay? So we're going to talk about the meaning of local. So we might be able only to go through some of this today. So we'll try to get through the conceptual part first, and then see if we have enough time to also to go through the actual mechanism and the trace. So a variable is local because of the scope of visibility. That means where can we see a particular variable? So that's the scope. Scope has to do with visibility. A local variable has the scope of the block statement in which the variable is defined. I'm going to highlight the whole sentence, because this is what I'm reading right now, and the significance is local variables can only be defined on a per block basis. They can only be defined inside a block, inside a block statement. They're only visible inside, but they also only live inside the block. So when you enter a block, the local variable starts to exist, but when you exit the block, the variable goes away. So once again, it corresponds to allocating and deallocating. When you enter a block that has local variables, the columns are allocated. When the block is done, those local variables are deallocated. So it's local in two senses because one is visibility and then the second one is lifespan. So both the scope and the lifespan are localized when we talk about local variables. Though not always the case, a local variables is also local in lifespan. In this class, we are not going to talk about local variables where the scope is local, but the lifespan is permanent. Okay, so we are simply not going to talk about those particular types of variables because there are applications of those kinds of local variables, but the application is very limited, and typically people misuse it because they think it should not be local when it is supposed to be local. So we're not going to talk about the other one. All right, so we're going to take a look at this program here, which looks awfully confusing. So a local variable is defined on line 7 here. It is also defined on line 2. So line 2 defines a local variable that only function f has access to, and it only lives when function f is invoked. In all other time of the execution of this algorithm, the local variable x that is defined on line 2 simply does not exist. Okay, so I just want to make that clear. Line 7 defines local variable x again in main. So now we have two local variables of exactly the same name, but there's no confusion because if your code is executing in main, it is referencing the local variable of main. If your code is executing in function f, it is accessing the local variable of function f. So they're both okay. So are we doing okay so far? Yes. Hmm. Yes. So when you look at the definition of a local variable or any variable, we start with the type of the variable. So this is one thing that we haven't seen before because we just say, oh, the variable starts to exist, when the algorithm starts. But from here on, that is not true anymore. Okay, so we can the the variable starts to exist when we see the definition, when we trace. Int stands for integer. Yeah. So int is the abbreviation of integer. It is telling us what is the type of the variable. X can only store integer values. So x by itself is a variable, but what it can store are integer values. Hmm. Which function are we talking about? Main or f? Looking at main, okay? So are you talking about this int here? That int is not explained yet. Okay, so we have not have the need to explain this int, which is defining the return type of a function. So until we talk about return value of a function, we don't have to talk about the return type of a function. So we're ignoring what is highlighted here on the projector. So instead, our focus is on this int of the local variable definition. So what this means is x as a variable can only store integer values. It cannot store the value of pi, for instance, 3.141415 and blah, blah, blah. It cannot store that, okay, because it is supposed to only be able to store integers, okay? And even so, there's also a range of integer values that you can store. In other words, from a math class, integers, there's an infinite number of integers in a math class. But in computer science, in programming, every integer type has a finite range. So it can only go from a certain negative value to a certain positive value, and that's it. Okay? All right. But we are not going to talk about that in this class. In CISP 360, the professor will kind of go into more details as to what value can we represent using an integer. All we need to do is to remember we can only store integer values. Okay, but the range is not as important in this class. We get all right. So line 7 is telling the compiler, that we need a local variable called x, and x can only store integer values. That's basically what line 7 is doing. Okay, and because it is a local variable x of main does not even exist until main starts execution. Okay, um, so this line here, okay, when you look at line 9, this x refers to the local variable of inside main that is called x. So it is referring to this particular local variable. It has no visibility of any other local variable at this point. Are we good so far? All right. And that's about it. Okay, so the syntax, the syntax description is down here. The trace is what is interesting about this particular algorithm. So let me go ahead and do the same trick here. Okay, so I want to um, display the algorithm in a smaller window while we go through the trace, by scrolling down. It may not work as well because the window oh, okay, it works okay. All right, there we go. So when we look at the execution of this code, execution starts on line 6 because main is the entry point of the entire program. Okay, we always start execution in a C++ program, with main. So there's not much to do on line 6 except that it is the beginning of a block statement, and we do have a local variable x within that block statement. So it is at the time when we get to line 6 that x starts to exist. So what do we do when we see the definition of a local variable? We allocate a new column. Okay, we allocate the leftmost available column. So at that time, the leftmost available column is this column right here. So we allocate it, but we also need to label it so that we know what that column is used for. And because we are allocating that column for local variable x, we just use x, which is the name of the variable, to label that column. Are we good so far? Allocation. And then we have to say, okay, if we are using a column, we better know what kind of things are being stored within that column. Local variables always start with unknown values. Okay, so in this case, x as a local variable starts with an unknown value, which is now represented by a question mark. Now, this part is actually very important, especially in C and C++ programming, because in C and C++, local variables always start with some unknown value. Does it have a value? Yes. Do we know what it is? No. It is some kind of integer value. We just don't know which one. Okay. So do not rely on, oh, local variables are always starting with 0. That in certain compilers, it might give you that impression, but that impression is not true based on the language description itself. Okay. So the language specification says local variables do not need to start with any specific value. That is the standard. Okay. Now, why this statement is super important is because in some other programming languages like JavaScript, local variables, or when you declare a local variable, it always starts with a particular value. But that assumption is wrong in C++ programming. Is that okay? So people who are transitioning from JavaScript programming into C and C++ programming always have to remember that, okay, because it is actually important. All right, so that's that explains what line 7 is doing. Okay, so line 7 is not actually executed. We count all of these as what line 6 has to do when we enter the block statement. So the next statement that we need to do is on line 7, which I forgot to write. That is my fault. There's supposed to be a 7 here. Okay, so I'll fix that after the class. So there's supposed to be a 7 where the mouse pointer is. So line 7 is the invocation of a function. So I hope by now this is going to bore you guys to no end. What are the 3 steps that we have to do when we invoke a function? Step one is allocate the next leftmost available column. So one column is already used for x, so the next available column is whatever is to its right hand side. So we allocate two. What do we do? Step two. Exactly. So since the call is on line 8, it is supposed to continue execution on line 9. Okay, and that's why we write 9 here. And what is the third step of invoking a function? We continue execution on the first line of the definition of the invoked function, which in this case is on line 1. Okay, so we continue execution on line 1. So line 1 doesn't really do a single thing. Okay, it is the beginning of a scope. Line 2 is the definition of the local variable. So it is at that time that we, once again, what do we do when we see the definition of a local variable within a block statement? Three steps again. Allocate the leftmost next available column, label it with the name of the variable, and three, to remember that the variable starts with a what value again? What is the value of a local variable in C++? Unknown, that is correct. Okay, so those are the three steps. Okay, one is allocate a column, two, label the column using the name of the variable. And then three is to remember it starts with an unknown value. So now we move on to the next statement, which is going to be the last thing that we talk about in today's lecture, which is line 3, which is also the most confusing line of the entire discussion of local variable. Because on line 3, we says, oh, let's put a value of 2 to local variable x. So now the question is, tag, we got two columns that are both labeled X. So which one should I use to update to a value of 2? The rule is it is going to be the rightmost column that is in use and labeled with the name of the variable that you need to access. So I'll say that one more time. You might need to write it down or locate that part in the notes because I wrote it in the notes too later on. So when you reference a local variable within a function, you always need to get to the rightmost column that is still in use, meaning it's not deallocated, that is labeled with the name of the variable that you want to access. So line 3 says, oh, we need to get to local variable x. The leftmost column that is labeled x is this column here, which is I'm, if I'm not using a spreadsheet, I don't have a really consistent way of naming which column, so I have to use a mouse pointer. This is the X that we're referring to on line 3, and that's why it is the one that is updated to a value of 2. The other column, okay, let me use the mouse pointer here. The other column that is labeled X is out of scope from the perspective of F, because this X is only in scope when you're in main. I'm not in main anymore, I'm in F. So F has no visibility whatsoever to the other local variable X. Okay, so we'll come back and continue with this discussion on um, Monday. Maybe Monday, maybe next Wednesday, because I need to time, the discussion of exam 2, because it's about that time to have exam 2. So I kind of have to evaluate whether to finish this topic or whether to talk about the next exam, on next Monday. Okay, but regardless, okay, either way, it is really super important that you spend the time to study and review the material. Can someone tell me again how many hours outside of lecture you're supposed to spend on each hour of lecture? 2. That is correct. Okay, so if you have been spending time, it's all good. But if you have not spent any time outside of the lecture to review the material, it is probably about time to get started with that habit. All right. I'll see you all on next Monday and have a nice weekend. hmm It just sounds strange to see you guys just once in this week, and then it's time to say have a nice weekend again.